Very good. We have found Kn. Then let's keep finding Bn for the later part. For now, let's discuss what this Kn implies. Now, well, we have such a formula, and you remember negative h bar squared over 2m d squared phi n over dx squared needs to be energy En phi n. Do you agree with this? Yes? So, what does it tell us? Remember, this is K. This is K. So, if you take the second derivative of phi n, then you are going to get negative K squared or negative Kn squared Bn sine Knx. Do you agree with this? So this tells you that En is h bar squared Kn squared over 2m, right? Hence, E of n is h bar squared pi squared over 2ma squared times n squared. This is the first time you have derived an energy quantization from actual equation. Remember the quantization of Planck? It was just arbitrary, not arbitrary, it was just, he was saying that if we want to solve this problem of ultraviolet catastrophe, then harmonic oscillator should have discrete energies, right? This time we are getting this from Schrödinger's equation, and it turns out that if you take a particle in a box, just simple, very simple particle in a box, it just can't stay still. Turns out that it can't stay still. The lowest energy that it can have is E1, which is h bar squared pi squared over 2ma squared. Then next energy level is E2, which is h bar squared pi squared over 2ma squared times 4. Okay, let me draw these two like this, and the third one is over here. Times 9. Do you see? And it goes on like that. So we get the quantization of energy from Schrödinger's equation for this particular system. Do you have any questions at this point? No questions? All right. Let's figure out what is Bn over here. So phi n is Bn times sine n pi over ax, right? What do we need to have? We need to have normalization because the particle has to be somewhere, right? So phi n star phi n dx integral from 0 to a needs to be 1. And we already did this. We already have shown that Bn star Bn needs to be 2 over a. Do you remember those times when we took sines and the next sign, etc., and we said that they are going to be this way? So in this course, without disregarding the phases, we are just going to say that Bn is square root 2 over a. So in summary, particle in a box summary, particle in a box summary. You have this situation 0 to A, and your energies are h bar squared pi squared over 2 ma squared n squared, and your eigenfunctions are square root 2 over a sine n pi over ax. Usually the way that we show this is that we basically plot a deep well, and we say that the energy levels are here, here, and here, and the ground state looks like this. The first excited state looks like this, and the third one looks like this. Okay? You must have seen this somewhere before. Have you? Yes? But usually it's just given to you from heavens, right? This is the way to derive it. Yes?
It's the oscillation of a rope, which is attached to two plates.
It's a bit different. It's a bit different in a sense that the oscillation of the rope, for the rope, the different frequencies actually have equidistant energies, as far as I remember. No?
Yeah, actually the rope has a mode of oscillations.
Yes, and they have. Sorry. I'm mixing up a lot of stuff. You are right. These are standing waves. That's how you remember them. These are standing waves. But in the context of classical standing waves, they have no energy attribute to them, no particular energy quantization, right? But for particle in a box, there is actually an energy quantization that goes together with those wave functions, with those standing waves. Okay? You have a comment? No? Do you have any question? Any question? Any comment? Actually, this is a nice place to talk about quantum confinement. Okay? Let's talk about quantum confinement. By the way, could we derive the same quantization making use of de Broglie's ideas? I think we could, but I will come back to this. Rewind, I didn't say anything, okay? Quantum confinement. So what is quantum confinement? As you can see, there are these energy levels like E0, let me call it E1, and then E2 is 4 times E1, and E3 is 9 times E1, right? Notice that, yes?
This year's Nobel Prize in Chemistry.
Oh, quantum dots, right? Very good point. Notice that, very good point. We should talk about that as well. H bar squared over 2 ma squared pi squared. So h bar is a universal constant apparently, right? Pi is mathematical constant. M is the mass, and A is something that we usually can tune, right? So you can put the particle in a narrow box, or you can put the particle in a wider box, or even wider box. So if you put the particle in a wider box, then the energy levels will be like this, let's say. Okay, I have to start small, so like so, okay? If you shrink it, then it will start from the top and it will go even higher. If you shrink it further, then it will start from even higher and will go to even higher. Okay? This is what we call quantum confinement. If you confine a particle, you start seeing more quantum effects. Right? The energy discretization itself is a quantum effect, and we can see more of these effects if we confine the system. You can see this also in other cases, like for example, you get a nanowire, let's say, silicon nanowire, and it has, in the bulk case, it has some band gap when it's really, really large. But as you decrease the radius, the band gap increases. Okay, there is this trend. Oops, sorry. There is this trend of band gap decreasing. So you can see, think of this as HOMO-LUMO level, highest occupied molecular level and lowest unoccupied one. They are far away from each other. If your system is really narrow, they start coming together if your system becomes bigger and bigger. But it doesn't mean that in the bulk systems, the band gap is always zero. It doesn't mean that. It just means that if you take something that is on bulk, has some band gap, usually increases if you make a nanostructure out of it. But I'm saying usually. You could take a silicon nanowire, not passivate it with hydrogen. Okay, now we are speaking nanotechnology, basically. Not passivated with hydrogen, then you have dangling bonds at the around the silicon nanowire, and then the system will become even metallic. Okay, so this band structure business is very tricky, and we should talk about it when the time comes. But right now, what you should learn is the word quantum confinement. If you confine system, quantization is enhanced. Okay? We can understand it also by looking at the wave function itself. So the wave function just tells us the probability of where the particle can be, right? So this kind of wave function is not acceptable, right? It has to have some hump. And the hump has to be square root of 2 over a so that it's normalized, right? The more you squeeze the wave function, the higher the hump is, right? Because it's square root 2 over a, the more the hump. And then the higher is negative d over dx squared. It becomes more wigglier. More wiggles, more energy. Okay? If you shrink it, the energy goes high. And so does the differences between the energies. Okay? Quantum confinement. Very good. Okay. Now that we got ourselves the eigenfunctions of the system, we can use them to figure out the time evolution of the wave function. Okay? How it's going to evolve mathematically. So I hope the particle in a box example gave you some idea about how you can derive ENs and phi n's. Let's say you have derived them. You have a set of eigenvalues and eigenvectors. Okay? And those eigenvectors have this property of forming a complete basis, right? They form a complete basis. What does it mean? Any function, any general function, f, can be represented as some coefficient times those functions. Do you remember this? Yes? Everybody? So, we can use this to find what's going to happen to the wave function at a later time. Let's say you started with a wave function psi x0, then you want to find what is psi xt. Okay? Then what you need to do is simply you need to find psi x0 equals to summation of Cn phi n. Okay, because notice that these functions depend on x and the left side also depends only on x. It's the function at time t equals to 0, right? So how can you find Cn's? Any ideas? No ideas? No, with boundary, who's speaking? You are speaking? You are speaking. With boundary conditions, we already found En and phi n's. So we have used them there. So let's write it down. Boundary conditions. But you are actually right in a sense that these are boundary conditions and this is initial condition. Very good point, actually. So my question was, how can I get these Cn's here? Well, to get those Cn's, please check your notes. We already did this in the math part. You simply do you simply do integral phi n star x phi x 0 dx. Okay? You do this integral. It's like to find the vector. It's similar to having Cn equals to phi n dagger f. If you remember that, we already talked about that. Do you remember that? So this is that. Okay. Any questions? No. So what I'm going to do is, okay, are we done? No, we are not done. The final piece of the solution is this. Once you know Cn's, then you can simply say that psi xt is summation of Cn phi n of x times e to the minus e I n h bar t. That's your whole solution.
Like each one is actually oscillating with their own frequency.
Exactly. So your eigen functions, like this one, this one, this one, I can't show it. So each one has its own rotation. The lower ones are rotating slower because they have less wiggles, right? The higher ones rotates faster, okay? And you define the initial function in terms of these wiggles, okay? And let's say you just have one bump, then most of the function will come from this one, and that function will oscillate slowly, okay? But if you have lots of wiggles in the original wave function, it will go like crazy, like that, okay? We happen to have a code. Did I click MATLAB? And yes, it didn't open, right? Something is happening these days with my MATLAB. Oh, it opened. I will give you an example.
There is actually
Okay, thank you. Actually, that's a very good suggestion. Okay, it is what it is. Let's continue with this one a little bit further. And so here is a new example. Okay, you have a system. And let's say you have solved the system in a way that you know ENs and phi n's. You already know them, okay? But this system starts in a wave function that looks like this. This is a typical exam question, by the way. Typical exam question. So it starts as a summation of the first eigenfunction plus the second eigenfunction. By the way, they don't need to be always like this, but they usually are, okay? Even if you have a harmonic oscillator, they resemble the functions of sines. They resemble them. They are not exactly the same. Usually you start with a one hump, then one node, then two nodes, etc. Now, can someone please explain me what this means, what I'm trying to say to you? Anyone?
State of the system is the superposition of
Yeah.
first and second.
Exactly. Despite the fact that they could be infinite eigenfunctions, we just happen to have a wave function that starts as a linear combination of only the first two. Okay? The cat could be moody, the cat could be jumpy, I don't know, grumpy.
But now it's
dead or alive, yes. Let's not be too morbid. It could be dead, but its wave function doesn't have that. Okay? It's either jumpy or moody. Okay? So when we open it, it's definitely not going to die. That's a good version of Schrödinger's cat. Anyways, this one has just phi 1 plus phi 2 and some coefficient a. The first question, it's a typical exam question. What is a? A equals to what? How can you find a? Do you understand the question? You are worried, but don't be worried because I'm already telling you how to solve it. So you will learn it. Then I will ask the same kind of question. So my exam can be perfectly it will be like example 1, example 2, and then the exam will be linear combination of those examples. Okay? So you don't need to know all the possibilities. Anyways, how would you find a? Well, you can use normalization. You can use the normalization and orthonormality of these wave functions, of these eigenvectors. Let's remind ourselves what was orthonormality. It means that whenever we take the integral of phi n star x with phi m x, we get Kronecker delta of nm. So it's 1 if n is equal to m. It's 0 if they are different. Are we clear? Yes?
Integrals limit is matter. So you should actually combine the same thing to
Okay. All right. Now, what was normalization? Normalization tells you that integral of phi of x0 star with phi of x0 dx needs to be 1. Do you agree with this? So let's put it together. So you have a star phi 1 star plus phi 2 star times a times phi 1 plus phi 2 dx equals 1. Did you follow this? So there are 4 parts. So this one will bring a 1. This one will bring a 0, right? This one will bring 0. And what is the final one? This one will bring 1. Do you understand this? Everyone? Yes? We are coming there. So there will be just 2 times a star a equals to 1, right? So a squared equals to 1/2. And in this course, a is 1 over square root 2. Yes? Good? Sure, of course. A, yes, A represents how moody and jumpy the cat is. So it came out 1 over square root 2, right? So we didn't come here to that point yet, but let me tell you. So our wave function starts like this, right? And these coefficients actually have some meaning. The square of those coefficients, the absolute value squared of those coefficients, actually tells you what is the probability of the cat being in that mood or in that state if you measure it.
Why we should get the power 2 of them?
Okay, you will see it. You will see it. Actually, I'm misleading you. I'm sorry. I take it back. Not the moody or that part. It's actually telling you. Wait. It's actually, these are probabilities if you measure energy. Energy. Okay? Because those probabilities change if you measure something else. Okay? These functions are special functions, and the coefficients, their squares, will give the probability of being at certain energy, and we will see it. We are getting ahead of ourselves right now. Where it is, the possibility of where it is. Let's. What have we found so far? We have found A, right? The question continues. Now the question is, you have found A, right? Let's also ask what is psi xt at a later time. What is psi of xt? Do you understand the question? Yes?
Maybe the other times, not initial.
Not initial condition, the other times, right? Now you are in luck because you know where it starts. It starts with 1 square root phi 1 and 1 over square root phi 2. So later on, what will happen is that it's going to be 1 over, okay, not enough space here. It's going to have 1 over square root 2 phi 1 times e to the minus I e1 over h bar t plus 1 over square root 2 phi 2 times e to the minus I e2 over h bar t. That's what's going to happen. Does it make sense to everyone? So you see, the initial condition actually matters here. it started as a linear combination of only the first two energy eigenstates. Let's start calling them that. And it continues being a linear combination of energy eigenstates at a later stage as well. Okay?
And it's again related to that wiggles. We have two wiggles.
Exactly.
Here.
Exactly. We start with a linear combination of two wiggles, and it stays as a linear combination of two wiggles. Just one wiggle moves slower, the other one moves faster. Okay? I happen to have this code, and we can start this code at a linear combination of the first one. Okay, maybe you need some increase in the font, right? I will describe this code, don't worry about it. This is just the initial condition, and it's a code of particle in a box, okay? So I've started as linear combination of the first one plus the second one. Do you have any? Thank you. Do you have any objection? No? So let's see how it goes. And I have to warn you, MATLAB is behaving today. Okay, this is what the wave function is doing. You are happy. Let me start actually from simpler state.
So you choose your wave function as a sine function?
Yes, initial wave function as a sine. Yes. Actually, let me simplify it and start only by this sine. Okay. So I'm starting with phi 1 only. And what do I expect? I expect it to have just phi 1 and just rotate. And that's what happens. So the red one is the real part, the blue one is the imaginary part, and it just rotates. And its absolute value stays the same. Okay? Why absolute value stays the same? Because absolute value of e to the I theta is 1. And it's the same function multiplied by e to the I theta, and I theta is rotating. Okay? If I start with 2 times pi, and this is the second one, and it will rotate faster. Do you see it? It's rotating faster. And I can start with the third one or 20th one. It goes crazy, right? Okay. Now let's put the same amount of the first one and the same amount of the second one. Okay. Then this is what's happening. You can see that in this case, it's not frozen. So if you start with a pure phi 1, pure phi 2, pure phi 3, it just remains in that state as an absolute value. Okay? We will talk about this. We will give a certain name to those states. We will call them stationary states because they are stationary if you look at their absolute value squared. Right? But if you start with a combination, linear combination of 2 stationary states, then it doesn't stay stationary, it goes back and forth. By the way, this is exactly what you would expect from a particle in a box classically. It would go back and forth. Like it would go to the wall, bounce back, would bounce back from the other wall, and go on like that, right? I think there is actually a homework question that connects the classical and quantum particle in a box in starting with this. What else can we talk about? Let me give you a sneak peek of what's about to come at a later stage. We will be able to make measurements in this code. Let me see what I press to get energy measurement. E. So if I press E, boom, it collapses to one of the eigenstates. Okay, I restore the wave function, which is not a real thing in real world. Now I have restored it to the initial condition. I will make an energy measurement. Boom, again the same one. Okay, restore, measure. Now it's the first one. Restore, measure. Now it's the second one. Restore, measure. Now it's the second one. So it's stochastic. That measurement part is stochastic. It can either collapse into the energy, into the state which corresponds to E1, which is slower, or it could collapse into the state that moves faster. Does it make sense? Restore, make energy measurement. Restore, make energy measurement. Now let's make position measurement. It can't be in the middle, definitely. So did you see? It collapsed into a certain position and then started going on. Restore. Let's do energy measurement. Then let's make another position measurement. It appeared over there. Does it make sense? Yes, let's do it. So when it's in the left-hand side, it's more probable to measure it in the left-hand side. Okay, ready? Okay. There is also still a probability of having it over there. So let's have another try. Okay, there you go. Okay. It refuses to come out. Okay. Okay. Maybe something is wrong with the code, but no, this one. So that's the thing. It's stochastic. You need to do it a million times so that you actually restore that probability distribution.
What happens if you wait long enough now?
Now, the code is not that perfect so that we see all kinds of things properly. What do you mean? Like some sort of dissipation or something? No, because the thing is that when you do position measurement and in the way that I have coded it, it's not very well coded. It's not bad either, by the way. But in principle, when it collapses into Dirac delta, you have all the energies there, right? So that's why it becomes spiky and it never returns into this smooth thing. That's why I smoothen it out by restoring the wave function. Okay? I think I also have momentum measurement, but then you get this wavy stuff. Restore, momentum measurement. Do you see? Restore, energy measurement, and it collapses into one of these. So what if you have combination of 1 and 3? Okay? Then it looks like this. And if I do energy measurement, then it either comes out as 1, the first eigenstate, or it comes out as 3. And this was an accident. We could have get 1 again. We could have gotten 1 again. I don't know if that's grammatically. But no 2. Yes, because we don't have 2 at the beginning. All right? Now let's look with 1 and 2, but let's put 10 of this, which would make it 100 times more probable than the other one. Okay? Don't worry about the normalization. I normalize it here anyways. Okay? But in terms of coefficients, I will put much more of 1 in there than 2. In that case, if I run it, do you see it goes on like this? And whenever I do energy measurement, it usually goes to 1. I did, and it went to 1. I did, it went to 1. I did, it went to 1. I did. You see, 100 times more probable, but let's do it enough times so that come on. Okay, this so gambling is bad for your health. So let's go with 2. So 4 times more probable of getting 1 than 2. Oops. Where is this E? 41, yes. Yes. Now it goes on like this. So if I do energy measurement, we got the second one, right? Although we had only 25% of that. No, 20% of that. So it's usually 1, you see? But sometimes it's the second one. Okay? Do you have any questions? We will play with this more and more. So if you think that it's a good place to stop, we can stop here. Do you have any questions?
Actually,
Yes.
I wonder what that means, the transition between 1 and 2 energy levels.
Yes.
What
So what is happening here? It's not actually the transition. We will talk about transitions later, but right now the particle is, first of all, it started as linear combination of being at energy E1 and being at energy E2. Okay? Since it started that way, it will always be, as linear combination of those two. So when you measure, it will be either come out at E1 or E2. Okay? About the transition, maybe you are talking about the wave function collapse. Right?
Yes.
That part we don't know. That's the part that makes the Copenhagen interpretation schizophrenic. We don't know what's really happening there. All experiments show that this is what's happening. Not really. We interpret our experimental outputs using wave function collapse. Okay? At the end of the lecture, if I will be healthy enough, we'll talk about many worlds interpretation. Okay? It's way above my, I don't know it very well. But basically, to me, it says that we are talking about many wave function collapse basically because of our limitations in understanding of quantum mechanics. And this is a key word, many-body wave function. Many-body wave function. So right now we are dealing with single particle wave function. There's only one particle, only one x and t associated with it. Okay? If you go to many-body wave function, then the words that you use are no different than all those people that are connecting with the universe, you know, like sending their message to the universe. Like you start going to that places, getting closer to there and more, because the many-body wave function in principle defines us all and our all possible fates. Okay, it's a huge thing. It's a huge thing. Okay, before we start a movement or something, let's stop the lecture. We will come back to this. But for now, we have this problem, and we are dealing with it as a wave function collapse.